Hi, my name is Marija. As you heard already, some of you, I work as senior ZK researcher in team 3327. This 3327 team is R&D department at Ethic42 company, but also I work as assistant professor at Faculty of Mathematics in Belgrade. And also I'm head of department of differential equations. And also I'm co-founder of Mathematical Academy. Mathematical Academy is some kind of private school where we are working with talents in the field of mathematics, physics, and cryptography. And for example, this year, our students, the best of them, obtained 41 medals on the state competition in math and physics. And last year, with cooperation with Ethereum Foundation, we organized probably the first zero-knowledge proof course on Balkan. So today, we will talk about ring learning with errors and fully homomorphic encryption Stealth Address Protocol. So today, we want to talk about private transactions, but also we want to talk about post-quantum cryptography. So let's start. First, we want to talk about private transactions. You know that blockchains like Zcash and Monero have some cryptographic methods and their core that enable privacy of transactions. But there is a great need to introduce private transactions on the public blockchains such as Ethereum. Okay? And when we are talking about privacy of transaction, what we mean by this? We want to hide the amount of transactions, maybe. Maybe we want to hide the recipient address or sender address. But maybe we want to hide all three things together, or maybe just one of them. And we can obtain this using different cryptographic methods. For example, we can use zero-knowledge proofs, like Zcash. We can use ring signatures, stealth addresses, or we can use fully homomorphic encryption. Today, we will talk about stealth addresses. And with stealth addresses, we want to hide the recipient address. So we want to have the same protocol that we have today, but only thing that we want to hide is the recipient address. So in order to obtain this, we need to have this structure. We want to have recipient. Recipient is Bob, and Alice is sender. So in order to obtain this, first thing is the Bob needs to do to generate some kind of stealth meta address. And after a generation of this address, he can send this address directly to Alice, or he can add this address in some kind of registry. So if Bob adds this address in registry, then everyone who wants to send the assets to Bob can go to this registry, calculate new address of Bob, and send the money to Bob. So every time, when every person wants to send the money to Bob, Bob will obtain new stealth address, okay? And after adding this address in the registry, Alice will go to the registry, find this stealth meta address of Bob, do some calculation, and after that, she will obtain new address of Bob, send the money to this address, and after that, Bob is able to control this address and to spend the money from this address. This is the idea, okay? And there are different ways to achieve this. We can use different cryptographic methods. Probably the most known one is this dual key stealth address protocol. Dual key stealth address protocol uses Diffie-Hellman approach. So you need to calculate shared key. So in this protocol, we are using multiplying scalars with a point on elliptic curve, and we have hashing in order to obtain the address, okay? And my friend Mihailo and I created two more protocols. They are using different cryptographic methods, such as elliptic curve pairing. So instead of calculation share key, we use elliptic curve pairing. Okay, and we have two protocols. One is with single key, and the second one is with double key. maybe we can mention here that we obtain this dual key stealth address protocol with elliptic curve pairing that we already implemented, obtain the best known results, better results than dual key stealth address protocol. Okay? And these protocols are really great protocols, but with these protocols, we don't have post-quantum resistant. So if we want to have algorithms that are quantum resistant algorithms, we need to use different technique. And for example, we need to use learning with error technique. So we used here ring learning with errors and module learning with errors technique and obtained two new protocols that are quantum resistant protocols. Stealth address protocols, but quantum resistant. And of course, we can use different way to achieve this. We can use fully homomorphic encryption to obtain this. And what was our motivation to do this? Well, we read the paper, base stealth address protocol. The authors of the paper are Vitalik, Tony, and others. And they already implement this and this. So they use dual key stealth address protocol. So they use Diffie-Hellman approach, okay? They implement these contracts, they use this elliptic curve, and they use view tag. View tag is just technique to for sender to calculate in a faster way his new address. Okay, just for optimization, nothing more. And in this paper, they want then on top of this have different schemes. They wanted that obtain the scheme with elliptic curve pairing and lattice-based schemes, so to use post-quantum cryptography. Okay, so we created these schemes because it was interesting for us to research this topic. Okay, now in order to explain our protocols, first we need to understand the basic concepts. So we need to explain some mathematical things. It won't hurt you, at least not much. So we will start. First thing, I think that the most of you already knows. In order to calculate public key from the private key, usually today, you need to multiply a number, your private key in the final field, with point on elliptic curve. So result of this multiplication will be the point on elliptic curve. Okay. And if anyone wants to obtain your private key from your public key, then he needs to solve discrete logarithm problem on elliptic curve. And this problem is very hard to solve. In real times, our computers cannot solve these problems. But quantum computer can. So we need to have different technique, and we will explain how learning with error technique are working. But here you can see we have learning without errors. So first, we want to explain the basic concept and to add some things to explain why we need to add errors in order to obtain this quantum secure algorithm. Okay? So I think that the best way to explain is with the example. So we'll start with example. We have here in the example Mihailo, and Mihailo has his secret key. This is Mihailo's private key. And in order to calculate a public key, Mihailo will not multiply this private key with point on elliptic curve. He will multiply public matrix, this matrix A, and these are elements of this matrix. This will be the first column, second, third, fourth. Okay? And the result of multiplication, this matrix with private key, will be Mihailo's public key. So this vector here will be the public key of Mihailo. Okay? When someone wants to calculate Mihailo private key from this public key, well, he needs to solve the system of a linear algebraic equation. So we will have 9 equations, okay? And 4 variables. But we already know that this system has unique solution because Mihailo has this private key. So it is enough to consider just 4 equations. And I think that everyone here knows to solve this system. We can use a Gaussian elimination method, or we can use here Kramer rule or something else. Okay, but we can solve this problem. So this algorithm is not secure algorithm. And because of that, we need to add errors. Okay, so let's talk about learning with errors. We will have the same example as we had a moment ago, but now we will calculate Mihailo public key in a different way. First, Mihailo will multiply public matrix A, the same matrix as we had a moment ago, with private key, same private key, and add vector of errors. Okay, so here we can see the errors. And what are these errors? Well, this error will be some numbers from some range. For example, here we use errors that are from range from -5 to 5, okay? And we will obtain, if someone wants to calculate private key of Mihailo using public key, this will be new public key of Mihailo, okay? And that person needs to solve this problem, and this problem is this problem. Just a sec. Okay. So we have 4 unknown variables and 9 equations. But we change the values on the right-hand side. So this system of equation probably does not have solution. And if someone wants to calculate Mihailo private key, then he needs to solve all system with all possibilities. And if Mihailo private key has a lot of coordinates, then we will have a lot of equations. And we have many possibilities with these errors. Okay? So it is very hard to calculate private key if you know public key of Mihailo. Okay? And we can make this problem even harder. What we can add? We can add modular arithmetic. So instead of using this as Mihailo public key, we can use module some number. For example, here we will use module number 89. So when we want to calculate this number 11, we will divide this number 3856 with 89. And reminder will be number 11. Okay, so Mihailo public key will be this vector here. And it's almost impossible to find out Mihailo private key if you know this public key, especially when you have a private key that has a lot of coordinates, okay? And this is impossible for our computers to solve in real time, but also if you have quantum computer, it is believed that is impossible too, okay? Now we want to talk a little bit about our protocol. So we have recipient, Bob, and we have Alice, sender. And first thing that Bob needs to do is to generate stealth meta address. Okay, in order to do this, Bob needs to generate his private key, and he needs to generate errors. Okay, so he will multiply public matrix with his private key and add errors, okay, and obtain public key. And this is if we use technique learning with errors. But here we use ring learning with errors. So we want to use polynomials in order to optimize. But you can think about technique learning with errors, and just to know there is one more step to obtain this protocol, okay? We don't have enough time to explain in detail, but just one step. Okay, and also Bob can generate viewing key. Viewing key here is not important for understanding. Viewing key is here that for example, you have a tax inspector and you want to prove to your tax inspector that you pay all taxes for all your transactions, okay? You can give him this viewing key. This is viewing key. And he can see all your stealth addresses and all your transactions, okay? So this is just for this, but it's not important for us today. After that, Alice will generate her private key and her public key. So she will generate private key and she will generate her vector of errors in order to obtain her public key, okay? And she will add this public key in ephemeral public key registry. But how Alice can calculate new address of Bob? We will use the similar technique that we used in Diffie-Hellman approach. So Alice will multiply here public key for viewing of Bob with her private key, okay? When Bob wants to calculate his address, he will multiply her public key with his private viewing key, okay, in order to calculate the same address. But both of them will not obtain the same results. Why? Because they add some errors. And Bob does not know errors of Alice, and Alice does not know errors of Bob. So both of them will obtain different results. And in order to calculate the same address, we need to cut off the last bits, okay? We can also have different technique. We can use technique that enables us to obtain the same result, but is more mathematical advanced technique, and we won't talk about that today. After that, Alice will calculate new stealth address of Bob, and Bob is able to control the assets using this spending key. This spending key is a result of adding Bob's private key with this share key that was calculated by Bob. So only Bob knows this private key, and only Bob can use this spending key. Okay, so we have post-quantum cryptography and stealth addresses in this protocol. And let's talk a little bit about fully homomorphic encryption. The fully homomorphic encryption is the holy grail of cryptography. So we know that more than 30 years ago, the first idea of fully homomorphic encryption is constructed. And 15 years ago, the first scheme is constructed. And why is important to use fully homomorphic encryption? Because with fully homomorphic encryption, the cloud or someone else can use your encrypted data, prefer some operation here over encrypted data and obtain also encrypted data. And what is here important, that if user use the raw data and do the same operation on raw data, he will obtain the same result when he decrypt this data. So no one else except the user needs to have decryption key. And this is very important, especially in the cases where we have some sensitive data, okay? And here we have just a history graph of fully homomorphic encryption. But today I think that the problems with this approach are optimization problem. So we have a scheme, but we need to do more optimizations. And now, for the end of this talk, I want to talk a little bit about fully homomorphic encryption stealth address protocol. And this protocol was constructed by Mind Network. And in this protocol, we have Bob. Bob is a recipient, and we have Alice. Alice is sender. And here we can see that this is a secret key for stealth meta address and public key for Bob meta address. And we can see here that in order to calculate public key, Bob obtained this public key as a result of multiplication. His private key with generator point on elliptic curve. Okay. This is interesting. And then they perform fully homomorphic encryption in order that Bob calculates secret key for this new stealth address. Okay. Here we have some different kind of keys, and we use fully homomorphic encryption, and Bob obtains secret key for his new address. Okay. But here, there is also one problem more. Why? Because here we have private key of new Bob's address, multiply by generator point on elliptic curve, and obtain public key for this new address. So we have the connection between private key and the public key using point on elliptic curve. So in order to calculate private key, we need to solve discrete logarithm problem on elliptic curve. But we already knows that this problem can be solved by quantum computers. So in their paper, they mention that this protocol is really a quantum safe protocol. But I think that is not true. What do you mean? So I think that using everything that we talk about today, you can change this protocol to really be quantum safe protocol. Okay? So this protocol have some vulnerabilities, but is easy to change in order to obtain post-quantum security. Okay? And this is everything for today. Thank you. See you.
Any questions? No? Okay.
Excuse me, I didn't understand the last part. Did you say that the paper presented did not offer post-quantum computing?
Yes.
It is because it is using elliptic curves?
Yes.
And is there another possibility in which it can be?
Yes, because in order to calculate private key of Bob using Bob's public key, we need to solve discrete logarithm problem. And it is proven that this problem can be solved by quantum computers. Okay? And here we have a problem.
So, which one of the two algorithms that you presented you think is more interesting in order to pursue? Because the FHE is so interesting because of,
yes.
Yeah, sorry. If you were going to tell somebody which one of the two start with, which would you say?
If I understand you correctly, I think that, yeah, Mihailo and I create two more protocols, ring learning with errors and modular learning with errors. And there is a difference just in number of dimension you need to use. So there are tools there already we have that we can use, and it is easier to use modular learning with errors. But ring learning with errors, potentially, if you're using, you can obtain maybe better better efficiency with ring learning with errors. But there are also some implementations that we can use. So for us, it is easier to use model. But in future, I think that better results we will obtain with ring learning with errors. And because of that, I talk about this protocol today. Thank you.
We're done. No more questions.
Okay. See you.